Okay, now let's start today's sharing and discussion. Firstly, I would like to invite Dr. Xie Xing to give a keynote. Dr. Xing Xie is a Senior Principal Research Manager of Microsoft Research Asia. Main research area is data mining and social computing. And he is leading the Microsoft Asia Open Collaborative Research Theme, Responsible AI. Today, his talk is Responsible AI Research at Microsoft Research Asia. Dr. Xie, please.
Yeah, let me share my let me share my slides.
Yeah, we can see that. Okay.
Yeah, let me start the captions. Yeah, I think you can see the slide now.
Yeah. And it works on the caption.
Good morning, good afternoon, and good evening. I'm Xing Xie from Microsoft Research Asia. First, I would like to thank all the audience and speakers for your great support for this workshop. Now I will first introduce the research conducted by our colleagues at Microsoft Research Asia, and I'm looking forward to hearing more exciting talks throughout the day. The breakthroughs in artificial intelligence in recent years have allowed us to see an incredible pace of innovation in this technology. We continue to see AI reaching human parity in machine reading, machine translation, general language understanding, and more. At the same time, the proximity of these AI technologies to human intelligence led to an unprecedented impact on the world around us. As our president, Brad Smith, wrote it in one of his books, the more powerful the tool, the greater the benefit or damage it can cause. Technology innovation is not going to slow down. The work to manage it needs to speed up. We all clearly see the power of AI, and we feel the urgency to develop technologies to help it be more responsible. A few years before, Microsoft created a set of principles to guide the responsible creation and use of AI. They are fairness, reliability and safety, privacy and security, inclusiveness, transparency, and accountability. Our research attempts to help algorithms meet all these different principles. With the further development of AI, the sizes of the models are getting bigger and bigger. For example, the recent Mac-Tron Turing NLG model has a record 530 billion parameters. Although these models are trained by public data, in real applications, in order to achieve the best performance, we often use user data or enterprise data to fine-tune the models. Due to the large noise to be added, as well as greater communication, computation, and memory overhead, big models have brought huge challenges for the privacy protection during both training and inference phases. In addition, because big models are often very complex and nonlinear, it's difficult for people to understand the working mechanism of the model and the reasons for the generated results. This also brings huge risks to their robustness and security. Finally, big models have been observed to inherit social bias and hate, so that applications based on the big models might further amplify these negative effects. At Microsoft Research Asia, we have conducted a number of research projects with the goal of making big model-based applications more responsible, in line with Microsoft's 6 principles. For example, we designed effective privacy-preserving methods to protect private data used for big model training or fine-tuning. We designed easy-to-understand model interpretation methods to let users understand how big models work. We remove or mitigate social bias and hate inherent in data when training big models. We also try to design methods to make big models more secure and robust in changing environment. Today, I will introduce how we approach the challenge of big models through a brief introduction to several of our recent works. First, I will introduce our work in the privacy domain. For AI privacy, researchers usually focus on 2 scenarios. The first scenario is that companies use their own private data to train big models and plan to share the trained models with the public. Here we need to ensure the privacy of corporate data while trying not to compromise the accuracy of the model. The second scenario is federated learning, which is a privacy-preserving method to train models on the data decentralized on a large number of clients. Each client keeps a local copy of the model and compute local model gradients with their local private data. A central server coordinates the clients and aggregates local gradients to update the global model. We have conducted research in both scenarios, and today I will introduce a few works in the field of federated learning. Researchers discovered that when protecting data privacy in AI applications, there is an efficiency, privacy, accuracy trilemma. In more detail, we help to optimize 3 types of goals. That is the degree of privacy protection, the performance of the model, and the communication and computing overhead. Unfortunately, in many cases, we cannot optimize all 3 of them at the same time. We believe that federated learning is essentially a multi-round knowledge flow. In each round, the global knowledge first flows from the server to the selected client, with the global model as the knowledge carrier. Then on the client side, we extract local knowledge by fine-tuning the global model using local data. After that, we update the local model as knowledge carrier to transfer the local knowledge from the client to the server. In the server, we will fuse the local knowledge together and update knowledge of the global model. We think this perspective can help to better understand our work as well as others' work. In traditional federated learning, the knowledge extraction model and the knowledge carrier model have the same architecture. If we want to reduce the communication costs by compressing the knowledge carrier model, the ability of knowledge extraction model will be weakened. In our work on FedKD, we explore decoupling knowledge extraction and knowledge carrier models. This work has published this year in Nature Communications. In FedKD, we use a large model for local knowledge extraction and a small model for knowledge communication between clients and the server. This can effectively extract local knowledge and reduce communication costs. We also propose a mutual knowledge distillation method to transfer local knowledge from knowledge extraction model to knowledge carrier model and the global knowledge from knowledge carrier model to knowledge extraction model. We show across multiple natural language tasks that our approach can effectively reduce communication costs when applying federated learning to the training of big models, while maintaining its performance as much as possible. In the federated work, we assume that all clients can train large models. However, federated learning involves a large number of users to collaboratively train a model, and the devices of different users may have different computing and storage capabilities. Probably not all devices can afford the same large models. If we only include strong clients and exclude weak clients, we will lose a lot of data and may cause some other problems like unfairness. In our work on inclusive FL, we propose to include all clients in federated learning and assign different sized models to different users according to their device capabilities. The underlying layers of these large and small heterogeneous models are shared, which helps to effectively fuse knowledge among them. Experiments on NLP datasets show that inclusive FL can achieve better performance as it can include all available users. Furthermore, inclusive FL can collaboratively learn large models on devices with heterogeneous capabilities through adaptive, affordable models and efficient knowledge fusion rather than simply learning small models that fit all clients. Through FedKD and inclusive FL, I described how we can reduce the communication overhead and the dependency on device capabilities. Now I will introduce that in some specific applications, such as news recommendation, we can significantly reduce the computational and the communication overhead through a deep understanding of the application. Personalized news recommendation is an important technique to alleviate the information overloading problem and improve user reading experience. Many deep learning-based recommendation methods have been proposed. They usually contain two core modules, that is, user model and news model. The user model is used to learn user representation from user historical behaviors. The news model is used to learn news representation from news content. With the success of pre-trained large language models, PLM empowered news recommendation methods have been proposed and achieve remarkable performance. However, it is expensive to directly apply a federated learning framework to these PLM-based recommendation methods, since the communication and computation costs could be too high for clients with limited resources. We propose efficient federated. In this framework, we decompose the news recommendation model into a large news model and a lightweight user model. Instead of training and communicating the whole model, in our approach, the clients only request the user model and the representations of the news involved in their local behaviors from the server. The clients locally compute the gradients of the user model and news representation on their local data and send them to the server for aggregation. The central server uses the aggregated user model gradients to update its maintained global user model and update the news model based on the aggregated news representation gradients. The updated news model is further used to infer updated news representations. This process is repeated for multiple rounds until the model gets converges. We analyze communication and computation costs of our efficient federated on a public news data set mined. This figure shows the average computation time and the communication overhead of each user per round. First, the average computation time of efficient federated is orders of magnitude lower than the baseline algorithms. This is because in our framework, users do not need to compute news models, thus reducing the computational overhead. Second, the communication overhead of efficient federated is also 5 to 100 times lower than that of our current approach. This is because in our framework, the users requests and sends the gradients and the parameters of the user model along with a small amount of news representations, which are much smaller than the gradients and the parameters of the entire model. Our current research focuses on protecting the data privacy in the most effective way while keeping the model as accurate as possible. However, we still have many fundamental questions unanswered. For example, how to define which data needs to be protected for privacy. It depends on the consequences and the societal implications of leaking the data. For example, until Google Street View Maps was used on a large scale, no one might realize that their daily activities could suddenly be followed by millions of people. Also, how to prove that the model really protects data privacy. For example, differential privacy, which everyone often hears, attempts to use a parameter to represent the degree of privacy protection, but not everyone understands what this number really means. In fact, as long as the data is shared, no algorithm can 100% protect data privacy. The difference here is how big the risks are and how to make users understand what those risks mean to them. In summary, we must comprehensively consider privacy protection, business value, public opinion, and personal needs to build a healthy society and business ecology. Just now, I present our research in the area of privacy protection. Let's move on to a different topic, transparency or explainability. An important angle for explainable machine learning is that we need to balance the fidelity of explanations with the cognitive load of understanding them. The larger the models or the more accurate the explanations, the more complex they become, and often beyond human comprehension. Therefore, we need to control the complexity of explanations and make them easier to understand. Our first task is try to give people a better understanding of the overall behavior of big models. Researchers have put a lot of effort into interpreting model predictions for a single instance with high fidelity. These methods have had great success in providing concise and faithful explanations. However, for machine learning practitioners, there's still a gap between fully understanding each instance and having a clear and comprehensive understanding of the overall model behavior. Regarding understanding the overall model behavior, we see two basic needs. First, while instance-level explanations are insightful, it's not feasible to examine explanation for all instances to gain a comprehensive view of big model. Existing methods address this problem by generating a global interpretation over the entire input space, or selecting representative local interpretations. When the target model is complex, global explanations often fail to provide concise or faithful explanations, but choosing representative local explanation depends on heuristic assumptions about which explanations are most representative. Second, researchers found that in order to achieve high human accuracy or generalized fidelity, we must clearly define the region to which interpretation applies. Otherwise, users can easily make wrong predictions about the behavior of the model on unseen instances by using incorrect explanations. We found that satisfying this applies demands correspond exactly to human cognitive processes. According to cognitive psychology, the main sub-process of the human information processing model are encoding, storage, and retrieval. While local interpretation methods help to faithfully interpret and encode individual information about an instance, users still need to distinguish important encoded information in order to store them correctly with limited cognitive resources. The user then needs to accurately reactivate the relevant information to make a decision. Based on these considerations, we define a framework called group-wise model-agnostic explanation. The inputs to our framework includes the dataset, the target model to be explained, and the cognitive budget. Here, the cognitive budget is the maximum number of explanations a user can examine. When the number of instances is much larger than cognitive budget, the users cannot check the local interpretation of all instances. In this case, we need to learn group-wise explanations that can be applied to multiple instances. The output of our framework is the group-wise explanations and their applicable regions. We have validated the effectiveness of our framework on different types of tasks. Earlier, I described how we can explain the global behavior of a model in a post-hoc explanation setting. However, we found that even with this capability, users may still have difficulty trusting the explanations, as they are always approximations of the model. Practitioners are generally uneasy when using these explanations. Also, it's difficult for us to integrate user feedback into the black box model. We need to consider indirect methods such as refining the dataset, which requires model retraining and is not guaranteed to meet the user's needs. We can see that the interpretability of black box model is inherently limited. To ensure close collaboration, both human and models need to improve. We came up with a new framework called SELOR, SELOR. SELOR is an acronym for self-explaining reasoning with logical rules. Self-explaining means that given a deep model, we reshape the model and upgrade it to a version that can explain itself. This sets the stage for close human-model collaboration. Explanations can faithfully reveal how models work because they are given by the models themselves and not approximated by other methods. Embedded interpretations also provide a handle for integrating user feedback. However, self-explanation is not sufficient to ensure mutual understanding. Without further constraints, these explanations are only from the perspective of the model and do not map to decisions that are reasonable for humans. For example, we might see interpretations like the input text contains the words is and an, and therefore has a positive sentiment. This results in low human precision. We define human precision as whether an explanation naturally leads to an output prediction based on human perception. An example of low human precision is N leads to positive sentiment. An example of high human precision is awesome leads to positive sentiment. Our user studies show that existing methods have low human precision. For example, over 30% of the explanation generated by SENN, humans were unable to correctly guess the model predictions. We solve this problem with logical rule reasoning. Logical rules consist of basic units such as words and logical connectives such as AND. They are very close to human decision logic and are widely used to make the predictions. They make it possible to achieve high human precision. Asking humans to define every rule takes a lot of effort and can introduce human bias. Therefore, we only ask humans to define the form of the rules, such as telling the model that the basic unit is a word and the logic connectives are and, or. The rules that lead to high accuracy and human precision are then automatically selected using deep models. Our user study confirms this. We found that on the adult dataset, seller was 5 times more likely to be selected by human as the best explanation compared to other post hoc and self-explanations. Furthermore, our prediction performance is comparable to that of the black box model, indicating that the interpretability of the deep model is not sacrificed by embedding interpretability in this way. Our research in the field of explainability focuses on how to generate explanations that accurately describe the behavior of a model, yet help humans easily understand and control the model. The key here is to understand how humans interpret their behavior and communicate with each other. There was once an interesting psychological experiment. In this experiment, the researchers had people try to jump the queue while using the copying machine. They found that people who were cut in line tended to show understanding when the other party could come up with a reason, no matter how strange the reason was, such as, may I use the copy machine because I have to make copies? However, we cannot build the same trust when we talk to AI. If artificial intelligence cannot provide accurate reasoning processes, humans often do not accept the result if it produces and cannot further develop human-machine collaboration. We believe we need to collaborate with researchers from different disciplines and on designing methods to build trust and partnership between human and machine. We have talked about privacy and explainability of AI. Now let's look at the values of AI systems. Recently, natural language technologies, especially the natural language generation technology based on pre-trained big models, have been developed rapidly. However, it has been observed that they often violate human values. For example, these models might generate toxic speech, as well as text with bias or misinformation. If these models are widely used in real life, they could lead to the spread of false information, inequalities of opportunity, create false beliefs, polarize opinions, and amplify distrust, and even incite violence, psychological and material harm. More seriously, researchers found that as the size of the model increased, ethical issues did not disappear, and even worsened. And tackling each issue individually may exacerbate others. This greatly increases the difficulty of solving these problems. We summarize the challenge in this area into 4 dimensions. They are performance, generation quality, flexibility and extensibility, and generation efficiency. An ideal approach should be able to remove bias in content and be able to adaptively align with human values while maintaining excellent generation quality and efficiency. In Microsoft Research Asia, we propose UDDIA a practical and unified framework for ethical NLG. With this framework, we seek to address multiple ethical issues simultaneously, with the flexibility and scalability to respond to evolving ethical issues. We are also working to explore the mechanism underlying harmful information and trying to develop better metrics and dataset for evaluating ethical problems. The UDDIA framework is essentially a tool to align AI with human values. However, we need a clear definition of human values. In different scenarios, these values might be very different. For example, last year, Facebook was accused of deliberately pushing hate speech to boost user engagement, reflecting a divergence between commercial and social goals. We need the collaboration of researchers in the field of sociology to deeply study the impact of AI systems on society. Ideally, if the topics of sociological research could be digitalized and described in a way that the machines can understand, it would be easier for us to embed human concepts of fairness, bias, and values into AI. We absolutely need the help of sociologists to make this happen. In today's work, I present some of our research in the areas of privacy protection, transparency, and ethics. Of course, there are many other potential directions in this field. First of all, because these directions are very new, there's no commonly agreed evaluation metrics, which makes it very difficult to compare pros and cons of different methods. We believe that developing an evaluation framework for responsible AI is essential to accelerate research in this area. Second, since the entire field is human-centered, we need to collaborate with researchers in the fields of psychology, sociology, and others to further deepen our understanding. Finally, most of our current research only focuses on one principle of responsible AI. This is not practical because they may eventually conflict with each other. We need to consider how to design a method that can deal with multiple challenges at the same time. Thank you. That's all for time. That's all for my talk, and I hope to discuss with you.
Thank you very much for this wonderful speech, Dr. Xie. Give us a whole picture of our recent research on privacy protection, explanation, and ethics on AI. Some of them are truly challenging, but also glad to see we have formulating and research work on this.